The easiest thing to do would be this. The easiest thing to do would be to take single amino acids like this and bring them in with sodium. So sodium, the diffusion of sodium, which is exergonic, provides the energy to actively transport in single amino acids. So we would call this a co-transporter here. If this dipeptide, so you see how we have a little dipeptide coming in here? If it is small enough, meaning that if the R groups on that amino acids were like a hydrogen or just a methyl group, so like valine or alanine, something like that put together, those are small enough that they can be brought in. But if that R group is too big, like tyrosine or something like that, which most of them are, it can't come in. So they have to be released as single amino acids. This can happen, but this is incredibly energetically expensive. This is endocytosis right here, and this is exocytosis right here. This is very rare. These small polypeptides by endocytosis. That doesn't happen very often. The reason it doesn't happen very often is that there are only some capillaries that are permeable enough that can absorb something this big. All right? So most capillaries would never be able to even absorb that. So if you can't absorb that, why would you do it? So it just doesn't make sense. But these two are the common ones. I like to think of it just this way. The reason I like to focus on single amino acids is because that's the most efficient, and that's consistent with our idea of having to reduce things down to that monomer, and the amino acid is the monomer. And even small amino acids, like alanine, valine, things like that, they're going to be brought in this way also. So it's just that if they are small like this, they can be brought in. But we just bring them in. And again, blood capillaries to the liver. So the liver is getting a rich supply after a meal of protein, amino acids, and of sugar. And the liver has to actively be removing those. You know, the liver makes a bunch of proteins, right? The liver makes all the albumins, all the serum albumins, and things like that that the body uses. The liver makes those, so it needs a rich supply of amino acids. And it also regulates the metabolism of amino acids via cellular respiration, so that it's always putting out into the blood all 20 amino acids all the time, so that every cell in the body has a source of amino acids. Now, tell me one thing for sure that's different if we talk about the digestion of lipids. What's difficult? What's that? So it bypasses the blood, so that's true. But it doesn't mix with water, and everything we've talked about has been all this chemistry takes place in water, so that's going to be one problem. It doesn't mix with water. And the other problem, as Tammy mentioned, is that it doesn't go to the liver. It goes into the lymphatic system, so it's going to bypass the liver. So if you did have a diet high in fat, then necessarily your arterial blood is going to be higher in fat, because the liver, it takes time for the liver to remove that fat as it gets it just indirectly. Okay? So what can we do to facilitate this? Well, let's first think about bile. Bile salts, the purpose of bile is to coat a lipid droplet, so to prevent it from coming back together. So for example, if you had a large, lipid like this, and in the stomach while we're churning and whatever, we break it down into lots of smaller little pieces like this, by the time it hits in the water and goes back to the duodenum, guess what? It's like that again. So that is a problem for us, right? So as this goes into the duodenum and gets mixed with more water, one of the things that we can do is take these lipid droplets after we've emulsified them here and just coat them like this. And we coat them with a salt, and this salt then prevents them from coming back together. So that now, instead of this happening, this doesn't happen, and we've done that. So that's emulsification by bile. Chemical emulsification, if you will. The significance of it is surface area. Right? That's all it is. So the role of bile, can you digest fat without bile? Absolutely. It just takes a lot longer. So the more fat you have in your diet and the less bile you have, guess what? You're going to have a hard time digesting. It's going to create cramping and things like that. So if you do have a problem with your bile, you better be eating a diet really low in fat, because you're going to have a hard time digesting that. It's just going to take longer. It's going to take a lot longer. And it's going to sit around and cause cramping, among other things as well. So we like to have this bile. The other thing we need, not only do we need bile to help coat this, but once we've done the bile emulsification here, we need digestive enzymes. And the digestive enzymes are these, lipase and colipase. They kind of work together, hence the name colipase. And what they do is they take a triglyceride and they, remove the fatty acids. So they're breaking these bonds here. They're called esters. And they're just releasing these fatty acids. We also know that we have this 3-carbon chain right here. There. And that's glycerol. Each one of these fatty acids is attached to a carbon. And that's glycerol. So we have the carbons in glycerol. We have the carbons in the fatty acids that we need to break down into small enough pieces that allow us to absorb them. Right? Because of their chemistry, they're actually, and the fact that they don't have to go into blood capillaries, they're actually a little bit easier to absorb than are the amino acids and the monosaccharides. So they actually